We now turn our attention to the evaluation of the magnitude of the hydrophobic character or hydrophobicity of molecules. Since hydrophobic interactions measure the relative preference of a molecule toward hydrophobic or hydrophilic environments, it makes a lot of sense to associate the measure of hydrophobicity with the relative solubility of this molecule in aqueous and non-aqueous environments. The hydrophobicity of any molecule is generally denoted by the symbol pi and can be estimated readily using a scale of hydrophobicity. The larger the hydrophobicity constant of a molecule, the larger the hydrophobic character of that molecule. One of the methods for the estimation of the quantity pi is a group contribution method. This method approximates the hydrophobicity of a molecule as the sum of the hydrophobicity constants of its chemical groups. So, for example, we can approximate the hydrophobicity constant for ethanol, CH3CH2OH, as the sum of the hydrophobicity constants for the ethyl and hydroxyl groups. The hydrophobicity constant for any group R is calculated using the following equation. This equation defines pi in terms of the relative solubility of any molecule Rx in ethanol and water. The quantities in bracket refer to the maximum molarity that these substances can exhibit in octanol and water. The above ratio is then divided by the relative solubility of the molecule HX in octanol and water. Note that pi is expressed as the decimal logarithm of this ratio of relative solubilities. Solubility of molecule A in solvent S is defined in a usual way as the largest number of moles of A that can be dissolved in a liter of solution of A in S. These measurements have been carried out for many groups R in a multitude of molecules Rx and are partially summarized in a table on the next slide. Please note that estimated in that fashion, the value of pi is independent of the choice of the group X. The table of hydrophobicity constant shows that the longer a linear alkane group, the more positive the hydrophobicity constant. Indeed, adding one methylene group raises the hydrophobicity constant by about half a unit. The table also shows that more compact, that is, more highly branched alkyl groups, do not raise the hydrophobicity constant as much as linear groups. For example, isopropyl has a hydrophobicity constant of 1.3 compared to 1.5 for N-propyl. This obviously makes sense since isopropyl would have less surface exposed to water than N-propyl. Along the same lines, the toluol or CH2 phenol group has a much lower hydrophobicity constant, 2.63, than what one would expect for heptol, 7 times 0.5 or 3.5. At the bottom of the table, negative hydrophobic constants are observed. These correspond to groups that are actually hydrophilic. The more negative the value of pi, the more hydrophilic the group is. In all cases, the hydrophilic constant is a direct measure of the incremental Gibbs energy of transfer of the group R from octanol to water. Indeed, when delta G is positive, the transfer is not spontaneous, and that is the case for all hydrophobic groups. Similarly, when delta G is negative, the transfer from octanol to water is spontaneous, and this is the case for all hydrophilic groups.